Good morning, everybody. We'll get started. So does this look like Jim Tressel? I don't know. Look like a... So it's funny. So about 10 years ago, a student said to me, they were like, oh, I saw this post, and it was from a student in the class said, if Dr. Kroner dresses up for Halloween, I will dedicate myself to the course for the rest of the semester and get an A. And I was like, really, just me dressing up for Halloween might actually change somebody's behavior in the class. So in the event that one of you guys were just waiting for me to dress up so you can dedicate the rest of your semester to this class, here's your opportunity. The other thing is that, so when I saw that probably 8 years ago or so, I think it was in 2016, 6 years ago, I dressed up as Woody Hayes, which nobody knew Woody Hayes even looked like in the class then. And I kind of think it's funny that Tressel was, if you're not familiar, fired in 2009, so it wasn't like that long ago, but probably long ago enough that you guys aren't familiar with that. But then he was fired for the Tattoo Gate scandal. If you guys remember, the Tattoo Gate scandal was some players had gotten tattoos just because they were football players. And that in 2009 was enough to get a coach fired, believe it or not. Now we just apparently give millions of dollars to players because they play football. So things have changed a little bit. But if you want a tattoo, I got some tattoos up here too. So I hope you guys have a happy Halloween. Now, one thing I'll say about Tressel was when he got hired, I'm from Youngstown. He was a coach at Youngstown State for a long time. I was super excited. And he gave this speech at a basketball game. And he said, in 310 days, you're going to be proud of our boys. And 310 days from then was his first Michigan game, which he won. So what I want to say is in 42 days, I'll be proud of you guys. Guess when we take the final exam. So, all right. So with that, we'll get back into chapter 8. And I hope you guys have a happy Halloween as well. I didn't get the memo that Friday was dress up day, apparently. I thought it would be Halloween. But anyways, okay, so we're getting back into the topic of Lewis structures. And if at any point during class you need some sugar, come grab some cookies. I'd rather not take 50 cookies back to my office. I might eat them all. But anyway, so Lewis structures. One way we can sketch Lewis structures is just to think of dot structures, but we're going to come up with some Lewis structures where it's going to be hard to do the dot structure. What I mean by that is something like CCl4, you can probably do that Lewis structure just by thinking of carbon's dot structure. And we had this issue with carbon of why 4 dots versus 2 versus 1, but I got 4 things I have to attach to it, so 4 dots around carbon might be best. And in one case, that's going to be why we have a more sophisticated set of rules, is it's going to be hard to know how to distribute these dots when we don't know the base structure ahead of time. But if I know I'm attaching 4 chlorines, and the chlorines are have 1 unpaired electron as well, so they have a chlorine that we might sketch this way, and then we have the other chlorines as well, we can probably come up with the Lewis structure simple enough. And then just pair up these unpaired electrons and make 4 single bonds, and then have 3 lone pairs around each chlorine. And that would be relatively easy enough for some structures. For some, it's going to get a little bit more complicated in terms of like things like SF4, SF6, or just in general, we might want a more comprehensive set of rules. So what if we first sum up the valence count? And that's just a general check too, that we should show in the Lewis structure all of the valence electrons for the molecule. So meaning if I take CCl4, I should be able to take 4 valence electrons per carbon, just from the periodic table count term coming up with 4, and then chlorine 7 times 4, 7 valence electrons for each of the 4 chlorines, that's 32 total. And if I'm wondering if this might be a valid Lewis structure, one thing I could do is just count the electrons. If I have a mismatch, then the structure would be wrong. But I have 8 electrons around each chlorine, and then times 4. So I have 32 electrons used for this Lewis structure. So this Lewis structure is showing the proper number of electrons. But if I want to follow the rules, one thing I can do is, like, the least bond I could have is a single bond. That's almost not true, but we'll dust that under a rug for now. But the least bond you would think you could have is a single bond. So you start everything with the single bond to the central atom. The book talks a little bit about how usually the lesser electronegative atom is the central atom, and that's not always usually the case. There are a lot of molecules like NH3 where nitrogen's more electronegative, but is the central atom. But in almost all cases, our Lewis structure starts, like our formula starts with the central atom, like CH4. So C is the first atom given. That's almost always going to be the central atom. And then the atoms after it are going to be attached to that central atom. So like NH3, 3 hydrogens onto that central nitrogen. So you can kind of get a sense if they're fluorines, those fluorines are going to be attached to that first atom. Sometimes it's a lesser electronegative, but it's usually like the first atom and then the other atoms afterwards attached to that atom. As we go along, we'll talk about a few organic molecules where we have multiple central atoms, but we'll look at those a little bit in this chapter, probably more in chapter 9 though, for having multiple central atoms. We're going to complete the octets, meaning 8 electrons each, or if it's hydrogen, just 2 total electrons around hydrogen for our non-central atoms. So if we're following the rules for CCl4, we'd be starting with our carbon, we'd be single bonding the chlorines by rule, and then we'd be putting a lone pair of electrons around the chlorines, which we'd already done, but this is just if you want to follow the more comprehensive set of rules, we'd be arriving at that same Lewis structure. And then the one thing that's kind of peculiar is you don't necessarily place electrons on the central atom unless there's leftover electrons to do so. So let's look at NF3 for an example of that. So if we're doing NF3, we'd have 5 for nitrogen. And this is, again, like the chapter 6 concept is how many valence electrons does nitrogen have? 2s2, 2p3. It's the entire n equals 2 is the outermost shell, so we have 5 valence electrons. And then plus 7 times 3 for fluorine. So that's 26 electrons. So if we follow the rules for NF3, we have a central nitrogen. We go 3 fluorines. We complete the octets of the non-central atom with lone pair electrons. Before we add 2 electrons to nitrogen, or before we know if we should add 2 electrons to nitrogen, we count. And so at this point, we'd count 8 per fluorine, 3 of them, that's 24 electrons used. And the 2 electrons left over are placed onto the nitrogen atom. So leftover electrons are placed on the central atom. In some ways, the reason why this might be the way we do the Lewis structure is there's really nowhere else on fluorine. We've like filled up its valence shell with electrons, so the next place we have to put electrons is on that central atom. And so if we look at SF4, let's do it next, kind of on this Lewis structure here. So we'd start with our count for SF4, 6 for sulfur, 4 times 7 for the chlorines. So that's 28 plus 6, that's 34 valence electrons. And so we're going to have a central sulfur, 4 fluorines. We do an octet around the fluorines. I prefer the dots, not the line. The line's not necessarily bad. Like some of you may want to write a line here instead of 2 dots. It doesn't make that much of a difference. I prefer the dots to think of 2 electrons as a lone pair of electrons. But if you do the lines, it's really not that big of a difference. And so that's 8 per fluorine, 4 fluorines, so that's 32 electrons. So we have 2 electrons left over. Those electrons are placed onto the sulfur atom. Now at this point you may be saying, okay, well you said we can't put the extras onto the fluorines because their octets are filled. Isn't sulfur's octet filled? And the answer is yes, kind of. That sulfur's octet looks like it's filled because it has 4 bonds to fluorine, meaning it's filled up its n equals 3 shell. But what the fluorines actually do here, and the compounds actually exist with this expanded octet on that central atom, are where that fluorine's actually making room for the electrons by being more electronegative. So this compound forms because the fluorine's like pulling the bonding pair electrons off of sulfur, and if on average they're pulling 2 electrons off of sulfur, they're making room for those other 2 electrons. So you actually make room for those electrons by the electronegativity difference between sulfur and fluorine. Yes?
Does it matter where you put the 2 dots?
Good question. So it doesn't matter on the sulfur where I'm actually writing them in. In fact, the 3-dimensional structure of these molecules shouldn't really be implied from these Lewis structures. So the actual shape of where these molecules orient these lone pairs and the bonding pair electrons is the topic of chapter 9. So chapter 9 gets into what do these molecules actually look like 3-dimensionally, and what are some of their properties then, like polarity, from those shapes. So for now, we try to draw most things flat. So you'll notice in chapter 8, almost all of our Lewis structures are like 2-dimensional, just because we don't want to get into that 3rd dimension until we know how to sketch it, or how to start thinking about that 3-dimensional shape. So just as long as the 2 dots are on sulfur, we could write them anywhere around the structure. Yeah?
But that's why they do the octet rule.
So sulfur in this Lewis structure violates the octet rule. So sulfur, we would say, has an expanded octet, and this is the, and there are a few other considerations that we want to make that we'll see to make sure that this really is the Lewis structure, but we'll see that this is the Lewis structure for SF4, and we would say that sulfur expands its octet in the Lewis structure. And the real molecule is smarter than the Lewis structure, right? The Lewis structure is assuming those bonds are equally shared, but those bonds between sulfur and fluorine aren't equally shared. If you imagine the fluorine's pulling the bonding pair electrons off, do you imagine how that's actually removing electrons from sulfur and creating space for those extra 2 electrons? So these molecules are smart. Like, you don't form a structure like SH4 in this regard because hydrogen doesn't have enough density to pull electrons away from sulfur to make room for those extra 2 electrons. So these molecules are kind of smart that expand their octets. We're also going to see that second row elements cannot expand their octet for any reason. So like if you're thinking about a Lewis structure for a second row like nitrogen, carbon, fluorine, those atoms cannot expand their octet. They're going to have a maximum of 8 electrons in the Lewis structures surrounding them. Third row, we can expand octets, but molecules that do so are going to do so for this reason of electronegativity differences. SF6 is another molecule that right off the bat you can imagine has to expand its octet because we have 6 fluorines that are going to have to attach to that one central sulfur. So the count would be 6 for sulfur, 6 times 7 for the fluorines. That's 42 plus 6, that's 48 electrons. And so this is a relatively simple Lewis structure where we just have the 6 fluorines single bonded. I mean, I probably don't have to write all these dots to know that they're there, because I'm just doing the same thing 6 times. But just to make sure we all see that we're writing 8 pairs of electrons on each fluorine total. There's 6 fluorines, so that's 48 electrons used, none left over. And so we have no electrons left over to place on sulfur, but sulfur still expands its octet because now we have 12 electrons surrounding sulfur. But again, it's due to electronegativity difference. Compounds with fluorine are common with expanded octets because these fluorines are actually pulling electron density off of sulfur, so it truly doesn't really have to expand its octet. And then that process is where you might imagine those bonds not quite being single bonds. Like that's where I said, the least bond you can have is a single bond. Well, how do you imagine this pulling electrons away? It's almost reducing that bond type for the sulfur-fluorine bond. Just a thought idea of how this compound's existing is by those fluorines creating room around sulfur by pulling those electrons off of sulfur. Okay, so we can consider multiple bonding if it minimizes magnitudes of formal charge. So we might want to think about formal charges in these Lewis structures. Let's start with CCl4. So let's start with this structure here. And there's a formula for this, but I think the easiest way to picture our formal charge is to formally break the bonds in half and then assess the charge that each of the atoms would bear if those bonds are exactly equally shared, where one electron's closer to one atom, the other electron closer to the other atom. And so if that's the case, the chlorines are 0 charge because they should have 7 electrons surrounding them for a neutral charge, and they have 7 electrons surrounding them. Carbon should have 4, it has 4. So usually in a Lewis structure, I'm not going to write 0 charges in for the atoms that are 0 in charge. What I want to specify in the Lewis structure is usually any non-zero charge. So if an atom doesn't have a 0 charge, I would want to specify it. What about NF3? Well, you can see NF3, again, if we break the bonding pair electrons in half, which is the concept of formal bonding. This is just the idea to give kind of, if the bonds are equally shared, then what would the net charge of an atom be before you think about electronegativity differences? So before we let electronegativity kick in NF3, we would predict that nitrogen here is 0 charged. That has a 0 formal charge. Now, what charge do you think nitrogen bears in the real molecule? Probably goes partial positive because the fluorines are going to pull the bonding pair electrons off of the fluorine, and the fluorines, which are 0 formally charged, are going to pick up that partial negative. So formal charge is breaking bonds in half and thinking about like the Lewis structure's charge, if you will, and then the actual charges are then thinking about how electronegativity differences play a role in sort of that bonding pair electrons not being equally shared. So it kind of lets go of that assumption of the bonds being equally shared.
Nitrogen has 2 electrons with it. Why would that not make it anything?
Well, so those electrons are just balancing into its total charge. So it's like it has that net 5+ charge that makes it out of its nucleus. It has about 5 electrons to fight for that charge. So the electron count is in balance with its nuclear charge is why. Yeah. So the presence of the lone pair doesn't necessarily make that atom negatively charged for that reason. Yeah. And so the actual charges on the fluorines would be partial negative. When we think about releasing the constraint, that looks like a positive. So partial negative. for the fluorines, and then a partial positive. And whatever, if you somehow knew the partial charge of fluorine in this molecule, you would know nitrogen would be triple that charge to put everything into balance. But again, that's just the thought of electronegativity, how that plays a role in the relative charges of these atoms. And then SF4 we did next. So SF4, just think about the bonds being cut in half. Sulfur has the 2 lone pairs, though, still closer to it, and then those 4 bonding pair electrons, so that's neutral. Single bonded fluorines are neutral as well, so the formal charges here are 0 as well all the way around. And the same thing with SF6, that sulfur should have 6 surrounding it, and it still does, because it has 6 single bonds, so 6 electrons, so a neutral charge. The fluorines, so a halogen with a single bond with all its lone pairs is neutral in charge in every Lewis structure. Well, I only wrote the formal charges in the others. So formal charges in the others are written as 0. Again, you could kick in the idea of electronegativity, and the fluorines would all go partial negative, and then the central atoms would go partial positive. I just didn't do that thought example in the other Lewis structures. But yeah, so like CCl4, same thing. The carbon would be partially positively charged. The chlorine's negatively charged with a partial charge. Okay, so now I think the only thing left to really do is see a bunch of examples, and then think about a few other concepts that we'll see, like, I'm blanking on the word, but we'll see it when we get there, yeah. Yeah. Okay, so let's just do a few examples to see, just some other examples. So like NH4, so 5 plus 1 times 4. The charge, we kick an electron off the structure, so we lose 1 for the charge in NH4. So we'd have nitrogen with 8 total electrons. So that's just 4 hydrogens single bonded. So this is just to show that for hydrogen, we're not drawing lone pairs. Hydrogen satisfies its octet, which is 2 electrons. And that's the proper number of electrons to be used, 8 as well. Now, where's the positive charge? So if there's a net plus charge, there should be something positively charged, or somehow the charges should add the plus 1. And that's nitrogen. So nitrogen should have 5 and only has 4 electrons surrounding it. So you see how, like, if we start with the dot structure for nitrogen, I think we're going to have a hard time getting to this Lewis structure. But if we just think of the rules, single bond, everything to nitrogen, and then count the electrons, there's none left over. And then we end up at our Lewis structure here, where our net positive charge, 5 minus 4. Nitrogen should have 5 electrons surrounding it, only has 4. So that means it has a net charge of plus 1. BH3, boron is the third element in the second row, so it only has 3 valence electrons, hydrogen 1 each, so that's 3. It's going to be hard for the boron to satisfy the octet rule when we don't have 8 electrons in the molecule, but BH3 actually does exist as a stable molecule, in part because when we single bond the 3 hydrogens, and when we notice that the formal charge, notice that the formal charge of boron is 0. Same thing with the hydrogens, of course. And so the molecule here is actually deficient of an octet, and that's okay. So molecules that are deficient of an octet, usually when you have a 0 formal charge, is usually a compound that's actually stable and actually can exist. And in some cases, you can bottle it and ship it. I don't think BH3 can actually be shipped. I think you can synthesize it and it's stable maybe in a flask, but then I think it decomposes relatively quickly. But I think BF3 is something you can actually buy commercially. If you replace hydrogen with fluorine and do mostly the same Lewis structure, so for BF3, it's this here, 3 for boron, 3 times 7 for the fluorines, so that's 24 total electrons. When we do our central boron, 3 fluorines attached, that's all 24 electrons. So notice that I've used all of the 24 electrons available. I have no electrons left over to go on the central atom of boron. So for both of these structures here, BH3 and BF3, you may have been thinking, well, why don't I put a lone pair on boron? Well, we don't put a lone pair on boron for, I think, 2 reasons. One, we don't have the electrons available to do so, so we'd have the wrong count of electrons. But then also doing so would make boron have a net 2- charge. And so if you think of nuclear charge, it's like the positive charge can hang on to electrons, and it's going to be hard for a positive charge of 3+ to hold on to a 5- charge. You can think that electron nucleus balance isn't there, and other things are going to come by and take those electrons away if we try to do that structure anyway. So if you're thinking, why does BH3 2- not exist as a stable ion? Probably because those electrons would rather be somewhere else. Same thing with BF3. We don't have electrons to go on boron, so we leave this deficient of an octet. So this is less than an octet, and that's okay. Especially when we notice that we have these 0 formal charges. Now with BF3, you might be thinking, well, why don't we make a double bond? Like, what if we did this? Could we do this and make this Lewis structure here where we do a double bond and move 2 electrons in there? Now, does this seem like it makes sense? At first glance, you might think this is good. If you like the octet rule and think that's some golden rule we need to follow, you might think this is a good Lewis structure. But notice what it does to the charges. It kicks a minus charge onto boron. So we took boron from what was a 0 to a -1 charge. Fluorine now should have 7 electrons surrounding it and only has 1, 2, 3, 4, 5, 6. So it removed an electron from fluorine on average and kicked its charge to plus. From what we know about electronegativity, this makes no sense. This is fluorine giving electrons up to a nucleus that doesn't even desire electrons to begin with. So fluorine wants electrons more than boron. It's actually trying to do the opposite. So it's not only not doing this step here, so let's undo all of that. It's actually trying to say, you know what, boron? I'm not even gonna let you have the 6 that you have. You know, like, not only am I not gonna let you have your octet, I'm gonna take the 6 away from you because I'm fluorine and I'm more electronegative and I can do so and pick up a partial negative charge. And boron goes partial positive. So if we're thinking about a Lewis structure that makes boron negative, you just start thinking about the positive charge, negative charge balance and the relative pull of these nuclei. Boron's bigger, fluorine smaller, higher charge, pulls those bonding electrons closer towards itself. Okay, so then lastly, COCl2. This is a weird one where you start seeing, okay, I have 3 atoms here. These are all going to be attached to the central atom, okay? Usually we're not gonna have these things in linear sequence. And usually when we do, we might make note of it, or it might be a class of compounds like organic compounds you'll come to recognize more easily. So whenever you see a Lewis structure with a couple atoms like this, 3 total atoms plus carbon, you're going to imagine that these oxygens and chlorines are all attached to that carbon as the one central atom, as opposed to being a linear sequence of atoms. The next thing is that we just follow the rules. Like the rules would be, do this, you know, do the lone pair on the non-central atoms. We might have counted first, or at some point we have to count our electrons. So for COCl2, we have 4 for carbon, 6 for oxygen, 2 times 7 for the chlorines. So that's 10 plus 14, 24 electrons. So for 24 electrons, this kind of looks a lot like BF3 in a way right now, but the difference between BF3 and COCl2 is that we have a positive charge on carbon. We have a net 0 charge in terms of the formal charges on the chlorine, 7 minus 7s. And then we have an extra electron on oxygen, so it should have 6 for a neutral charge, and oxygen surrounded by 7 electrons. So that makes oxygen negative charged. Now, this isn't a terrible Lewis structure. This may not just be the best Lewis structure. This one here, we can actually imagine making this double bond. One of the rules that we glanced over on the previous page, it's harder for me to flip back, but if you guys look back at the previous page, it's like consider multiple bonds if it reduces the magnitudes of formal charge. So if we can reduce the magnitudes of charge through a double bond, so I move these 2 electrons into a double bond here. So I still have 24 electrons used. I've just moved 2 of the electrons from being on oxygen to being a double bond. That what I've done is I've changed the formal charge of that oxygen now to 0 from -1. So we've gone from -1 to 0, and carbon's now 4 minus 4, so it's also 0 instead of positive. So the magnitudes of charge have been reduced. So we went from -1 plus 1 to 0, 0. So it's okay to do that, that's good. We want to do that in a Lewis structure. We don't want to go from 0, 0 to -1 plus 1. We don't want to maximize charges just to try to satisfy the octet rule. And so this structure here ends up with carbon satisfying the octet rule, all the atoms satisfying the octet rule, and then all the atoms having a 0 formal charge. Sometimes you'll see an idea, and I don't like it worded this way, but some old exams, predominantly the department ones you'll see, the 3 practice exams they'll put up. Sometimes you'll see something referred to as the formal charge rule. The formal charge rule is just the idea that you try to minimize formal charges in a Lewis structure, or if you're evaluating 2 what appear to be equivalent Lewis structures, you go with the one that minimizes the magnitudes of formal charge. We'll see that come up in a couple. I don't know if it's a rule so much as it's a concept that reducing formal charge is what structures tend to do. Okay, so let me throw this to you guys. So Lewis structure of which molecule here contains a central atom with one lone pair of electrons? So consider nitrate versus sulfite. I'll give you a couple minutes to think about this one. I see a few of you still writing. I don't want to go too fast, but nitrate. One thing I would recommend as we start doing Lewis structures, try not to memorize Lewis structures. It's easy enough to come up with those structures. Yeah.
5 plus 3 times 6, where do you get 1 extra?
Yeah, so the one extra is from the charge. So that extra electron goes into the valence shell. So we have 5 from nitrogen, 3 times 6. If we didn't have the minus charge, we'd only have 5 plus 18. But the extra minus charge is 1 extra electron that goes into the valence shell. And so we add an electron with the minus charge because that's adding a negative electron to the negative valence of the molecule. And then if you have a positive charge, you take electrons away. So for NH4 plus, remember, we took an electron away for the positive charge.
So oxygen is stealing from nitrogen in this case?
No. This is not stealing. It's just NO3 minus in terms of the balance. It's just thinking the valence count of nitrogen is 5. The valence count of oxygen is 6. There's 3 of them. And if we didn't have if we just had NO3 without the minus, that would have 23 electrons. NO3 minus, we have to have that extra electron. So it adds 1 more electron. It's like saying fluorine has 7 valence electrons, F minus has 8. So,
I need to count that, but oxygen is only 6 valence, but by sharing, it's trying to pull.
oh yeah, so we haven't finished the Lewis structure. So this is how I would start. So find the central atom, single bond the oxygens, give the oxygens an octet, the non-central atoms an octet, then count electrons up, see that there's none left over. So for the sake of the question, there's no lone pair on nitrogen. So for the sake of the question, we may not have to finish the Lewis structure because we see that there's no lone pair on nitrogen because the question is saying which Lewis structure has a central atom with a lone pair. So there's no lone pair on nitrogen. So for the sake of the question, we can be done with nitrate. We'll come back to it in a second though. So for sulfite here, SO3 2 minus, we have these 2 extra electrons. So once we distribute our 24 electrons around 3 oxygens, we have 2 extra electrons to go on to sulfur as a lone pair. And so only 2 here in terms of the question being asked would have a lone pair. Now, an interesting question is, are these Lewis structures done in terms of these being the best Lewis structures? For nitrate, not yet, because we have a 2 plus charge on nitrogen. We have a minus charge on each of the oxygens, so we can make a double bond. So we can make a double bond between an N and an O, and that reduces the formal charge to now be plus and 0. So through making 1 double bond, we reduce the magnitudes of nitrogen and oxygen. But then we have to stop here. We can't continue. Even though there's charge in balance, we can't continue because we can't expand the octet of nitrogen. If I were to try to go to the O double bond N double bond O here like this and do it again, I've expanded the octet of nitrogen. I can't do that. So the limit on nitrogen being in the second row is 8 electrons in its valence. So there's no way we can expand the octet of a second row atom through continuing the process of making double bonds. Now we have to talk about resonance. We'll talk about that in a minute. That's a concept that double bond is going to resonate through the other two oxygens. Let's come back to that in a minute. But let's talk about sulfite before we move on from this question. So for sulfite, we could be done. So if we look at our charges here, negative for the O's, we have a positive on sulfur. Sulfur's 6 minus 5 for plus 1. And so we could make a double bond because sulfur is in the second row. So second row atoms can expand their octets technically, or through some structures they can do so. So we actually arrive at two different Lewis structures. One that minimizes the magnitudes of formal charge. So this is the so-called formal charge rule Lewis structure because it minimized the formal charges of sulfur to 0 and 0 for the oxygen. Again, we have to talk about resonance, but we'll talk about that in a minute. And then we also have the octet rule structure, which is the one we started with the lone pair on sulfur and lone pairs around the O's. So this is the octet rule Lewis structure. And so I think the octet rule Lewis structure makes more sense. It's hard to pack electrons around the central atom, especially when you're talking sulfur is not very electronegative. It's hard for it to pull electrons in towards itself. And even if it did, oxygen's going to try to steal them back anyways. So for the most part, the octet rule structures are the better Lewis structures. In fact, when I didn't have to have these common exams with other instructors in Gen Chem, I would say you never expand an octet just to minimize formal charges. But my colleagues think that you can say and ask a question that might be asked this way. For sulfite, like how many double bonds are in the Lewis structure that uses the formal charge rule or minimizes the magnitudes of formal charge? And if that's the question, then it would be one double bond. So you'll see questions kind of say in a Lewis structure for something like sulfite that follows the octet rule, and it would be the top Lewis structure, this one. You'll see other questions that say for sulfite satisfying the formal charge rule, look more like this structure here. So you'll see questions that kind of get at these two different Lewis structures. I think this one's better, but whatever. But this will be a couple Lewis structures as we continue. So let's talk about formal charge. Let's just go back to formal charge for a minute, make sure we're on the same page here. So for iodine, what's the formal charge of iodine here? So think about this for like 30 seconds. So again, the concept of formal charges is we're breaking the bonding pair electrons in half. So half of them are closer to one atom, the other half to the other atom. And then the non-bonding electrons stay on like iodine. So iodine has 8 electrons surrounding it. Should only have 7 for a neutral charge. So 7 minus 8 is a net minus 1. So hopefully you guys agreed that iodine's a minus 1 here. Another thought is that if the overall, like when I write the charge minus here, means that there's a minus charge somewhere in the Lewis structure, and I just haven't identified where it is. So when you see a bracket with the minus, means this is ICl4 minus, and that there's a minus charge somewhere, and that the chlorines here are all 0. We've seen this Lewis structure a bunch of times. So if the chlorines are all 0, and you know they're 0, that means iodine has to be minus 1 in order for all those charges to add up to the total charge of minus 1. So a few ways to the formal charge. Like this question here, this page is going to get at kind of comparing formal charge, oxidation numbers, and actual charges. So let's think oxidation numbers first. This is from chapter 4. So oxidation numbers just come from chapter 4. So for like hydrogen, it's +1 in molecular compounds. Oxygen's -2 with some exceptions, but this isn't one of the exceptions, so that'd be -2. Let's actually just go through the oxidation numbers like we did in chapter 4. Remember how fluorine's always -1? Oxygen therefore goes +2 to pair up and balance. And we had talked about in chapter 4, this is because fluorine's more electronegative, but we said, well, we haven't defined electronegativity. Now we have. We see fluorine wants electrons more than oxygen. It should bear the negative charge. PF5, fluorine should be minus, so phosphorus goes +5. And then chlorine goes positive, -1 for fluorine, so +3 for chlorine and ClF3. Now let's just compare the magnitudes and the signs of these charges with each other from formal charge versus the actual charges. It's the actual charges we really want to compare and see that generally we're getting the same sign, negative and positive. So everything about water, so we're going to have central oxygen, 2 hydrogens attached. I'm drawing this bent. We'll talk about why it's bent in chapter 9. But if you're wondering about molecular structure, that'll come up in the next chapter. I would have 2 plus 6 for 8 electrons in the Lewis structure, so I have 4 here, so I have the 2 lone pairs. You can get this structure from a dot structure as well. So formal charges here, 0 and 0, but we know that oxygen's more electronegative. It's going to pull the bonding pair electrons closer towards itself and go negative, and hydrogens go positive. And so notice that the sign of the oxidation number being positive for hydrogen matches the actual charge we expect for hydrogen in the real molecule. So the oxidation numbers are really helping us predict oxygen's going to be the negative atom, hydrogen the positive atom. The same thing in OF2. OF2 probably looks like a strange Lewis structure. It's actually pretty easy because we just have 6 plus 2 times 7, 20 electrons. So if you just follow the rules, you end up with fluorine on either side of oxygen, single bonded to their central atom. And then that's 16 electrons, 4 electrons left over, go on to oxygen. And so then this Lewis structure here would have 0 formal charges all the way around. 6 minus 6 for O, 7 minus 7 for fluorine. But then the electronegativity kicks in. So formal charges allow us to think about charge, then electronegativity. So it's kind of like, what's the charge before we consider electronegativity? We kick electronegativity on. Fluorine's more electronegative, goes partial negative. The oxygen goes partial positive. So notice that we're predicting minus and plus for fluorine and O, respectively, in OF2 from the oxidation numbers. So the oxidation numbers are telling us the right signs. So if you know the oxidation numbers, you can probably predict the partial positive and negative signs for the atoms in the molecule. PF5 just has 5 fluorines. I'm not worried too much about the geometry of how I'm attaching these, just somehow I'm getting 5 fluorines around. In fact, I'll just do that because it's going to be 8 times 5 electrons, that's 40. And then I have 5 plus 7 times 5, that's 40 electrons. So I have none left over to go on the central phosphorus. So just 5 PF bonds. And then, again, we're predicting 0 formal charge. 5 minus 5 for phosphorus, 7 minus 7 for the fluorines and their formal charges. But the real charges go negative. So all the fluorines would have a partial negative charge, and then the phosphorus a partial positive. So again, recognize we're predicting the right sign from our oxidation numbers, that phosphorus should be the positive atom, and it is, and fluorine should be the negative atom, and it is. And again, recognize that the full negative charge from that the oxidation numbers aren't telling us the true charges because these compounds aren't ionic. So it's just like a bookkeeping system, but it's a bookkeeping system that's getting the proper charge right in terms of the sign on the right atoms. So ClF3, so chlorine 7, fluorine 7, so that's 28 electrons. So central chlorine, 4 fluorines. So that's 8 per, so that's 24 electrons. So that's 4 electrons left over. And so chlorine looks strange, but it's still 7 minus 7, right? It's 7 minus 1, 2, 3, 4, 5, 6, 7. So the charge on chlorine, 7 minus 7, that's neutral. Fluorines are all neutral as well. So not every stable compound is going to have 0 formal charges all the way around, but a compound that has 0 formal charges has a good chance of being something that's pretty stable because we have like the right balance of charge. We don't have anything that has too much charge or too little charge. If we did, they might be trying to find some other structure or way to exchange electrons with some other substance to get those electrons more in balance. But so then the electronegativity kicks in, fluorines go, of course, partial negative. So the reason why fluorine's always -1 in compounds is because it's the most electronegative element. It's going to win the battle for electrons and pick up more negative charge than the atoms it's bonded to.
17.
Well, it's the negativity trend. So if you look at the chart, fluorine just has a greater desire for electrons. It has a greater electronegativity. So it's, if you just, in the concept of electronegativity would be smaller the size, relatively high charge, able to pull negative particles in more closely. So it's really about its small size that gives fluorine its especially high electronegativity. So chlorine technically has a higher effective nuclear charge, but it's bigger. So it's harder because chlorine's bigger for it to pull electrons in towards itself. So what does chlorine and bromine and iodine in is their size. So fluorine being small and relatively high in effective charge makes it the best. So I don't know if we would have predicted fluorine without knowing anything would be the highest electronegativity, but once we see that it is, we can explain and think about its small size. It really dictates that trend. The size versus charge is an interesting trend. Like if you look at electron affinity, it's actually chlorine's more negative. So like chlorine being relatively bigger, more charged actually made it greater in absorbing an electron. If you look at if you look at ionization energy, fluorine's the highest. So iodine's kind of the easiest to lose an electron. So there's a lot of ways that this battle kind of is fought in between atoms. But in terms of bonding, through like single bonds, fluorine wins the battle. Yeah.
How is fluorine able to hit my battle against chlorine? It has atomic number is 9, whereas
It's the Ohio State, hopefully, in the battle. Not that state up north. Okay, so let's come back to like things like nitrate. So I'm going to go back to the Lewis structure that we had earlier and start to think about this. In terms of a concept of resonance, of why this Lewis structure, like why not make the double bond here and put these electrons here. And then if I do so, that would have this double bond here. And I might use this little arrow to indicate this concept of electrons kind of moving around the structure. And then why not here? So if I did that, then I'd have the double bond over here. And this leads us to a tricky concept. Let me make sure I put some charges in here. So the nitrogens are always positive because they're always the same in these structures. And then the oxygens with single bonds are minus. And then the oxygen with the double bond is 0. I'll just leave the 0 oxygen unmarked. Okay, so this leads to an interesting concept. And the concept is for Lewis structures, they're not real. You know what I mean? Like, they're a model. And so for some structures, the model is really good. You know, like for CCl4, the Lewis structure model like represents a molecule really, really well. For nitrate, it turns out that the one Lewis structure just isn't a great model. So when we start thinking about Lewis structures, if we start to think that molecules really are the Lewis structure, that's actually the wrong idea to take. The Lewis structures give us an idea to represent molecules for us to think a little bit deeper about their structures. The case for molecules having equivalent Lewis structures, like these are all equivalent to each other. They're just not identical. And they're equivalent in a sense that if you imagine the energy of one of them would be the same as the others. If you imagine the properties of one, it would be the same as the other. So they're equivalent what they represent, but different from each other. You know, they're different in terms of which atom's making the double bond, like which of the oxygens in the structure is making the double bond. And so whenever we have the case of equivalent yet different Lewis structures, the real molecule exists as like the composite or the average of these structures. So it exists as the average of these resonance structures. So the concept of having resonance are when we have these equivalent yet different Lewis structures. LS for Lewis structures. So equivalent yet different Lewis structures. Whenever we spot this, the real molecule exists as the composite, the averaging of those Lewis structures, and never as like A then B then C and going back and forth. So this isn't like an equilibrium. This is, at all times, nitrate actually will look more like the composite. And so the composite is a little bit hard to picture And it's a little bit easier if we go to the structure. The structure turns out to be like a triangular plane. But if you imagine the structure here, it's just kind of where each of the oxygens between nitrogen picks up that extra bond like a third of the time. So if we look at the molecule, it's like we have this one bond, this two bonds, 3 and 4. So I have like 4 total bonding pairs of electrons spread across the 3 NO bonds. So notice I have 3 NO bonds in the molecule, and I have like 4 bonding pairs of electrons that are going to distribute across them at all times. So this is what the average equals to. So the average bond is like a 4/3 bond. Now this gets into a concept of like bond order that we haven't talked much about. This would just be a simple idea though, that like a double bond, it has a bond order of 2, and a single bond has a bond order of 1. So this means these bonds are getting closer towards double, but they're still kind of like single. They're somewhere between a single bond and a double bond in terms of their property. But the key is more than the bond order is that all of the bonds are the same, and that therefore all the charges on the oxygen are the same. So it's really not minus, minus, or 0. It's really minus, minus, or 0 averaged out. So the average charge on each of the O's, well, it's -1, or it's -1, or it's 0. Divide by those 3 possibilities, which would be -2/3. And this is what the real molecule would look like. So it would never look like it has a shorter bond and 2 longers. It would always look like at all times like it had 3 equivalent length NO bonds. So all the bonds are equal in length. So all their bond lengths are the same. Double bonds usually shorter than single. It's not the case that one of the bonds is double, the other 2 are single at any given moment. They're always 4/3 bonds. It just gets into the idea, like the most confusing part is you sketch the Lewis structure, you think the molecule does that. The molecule doesn't do the Lewis structure just because we wrote it. The Lewis structure is like a model that we came up with to try to understand the structures, and the real molecule is going to take on a compositing or an averaging of those structures. It's how the molecule truly behaves. So we just have to get out of our mind that sometimes a Lewis structure that we write is compelling a molecule to do that structure, to exist as that structure. And sometimes it's a hard thing to imagine. If you go back to a single Lewis structure like CCl4, a lot of our Lewis structures, there's only one Lewis structure, and you can think, well, the average of 1 is just the 1. So the rule kind of still applies to structures that don't have this resonance effect, because the averaging of one Lewis structure is just the one Lewis structure. So most Lewis structures without this issue look exactly, the molecule will kind of behave and have the bonding that we're picturing. It's just these resonance cases won't. PO4 3-, this gets into a slightly different issue, kind of like the SO4, SO3 2- problem of do we actually do the extra double bonding? So we do 5 plus 4 times 6 plus 3 for the 3-, that gives us 32 electrons. I think our best Lewis structures are PO4 being all connected with 8 electrons around each O. That's 32 electrons, none left over. And so we have no electrons left over. Positive charge on nitrogen, negative on all the O's. And that this is a particularly good Lewis structure. Now we don't necessarily need to invoke making a double bond, but if we did, that we have to picture that we're going to have resonance taking place. That we're going to have that double bond resonating through the structure. I think one last quick slide for today is that this is actually a slide out of chapter 9 that shows the reasoning behind the averaging out of those Lewis structures is delocalized bonding. This is a picture we'll understand a little bit more when we get to chapter 9, but what we get is actually all like sort of 4 orbitals between the N and the O's kind of simultaneously overlapping at one time, such that you get kind of like one orbital that's hanging on to that extra double bond and spreading it across all 3 atoms simultaneously. And it's never like a double and 2 singles. So it really never is the localized double bond, but it's always a delocalized averaging effect through resonance. So I think we're going to get a demo here in a minute. They might be waiting for me to stop talking. They might be listening behind the door. There's going to be a pumpkin that comes out that we're going to try to blow up.
cut the cookies. And it's your job.
After the demo, feel free to come up and get some questions.
Nope, you gotta go.
Or a tattoo if you want. I'm gonna get into my costume for this too.
Have you prepared them for the board to be including pumpkins?
I have not. We explode a cookie too.
So today we are going to use science to carve jack-o'-lanterns.
I forget what the byproduct is. But so calcium carbide plus water is making some acetylene. What does acetylene do with oxygen in the spark? Well, I guess we'll see. Jim Tressel's gonna watch.
Alright, this is Brandon. This is his first pumpkin.
Told me it's really quiet, and I should like keep my hand right here.
Well, I should say we're gonna use chemistry to carve the pumpkin, right? Like
What's that?
we're using chemistry to
No, we
finish.
are.
Yeah.
We're making a settling gas and then we're gonna light it on fire and it's gonna be glorious.
It's the useful side of chemistry to carve pumpkins. You want the lights down more? Or is this good?
We can turn that more. So it's pretty loud if you're close. Feel free to cover your ears like this, like we do for the hydrogen balloons. So we're just waiting for the gas to build up. And it's real hard to time exactly how long we have to wait. So we always have to stall a little bit like this. Sometimes if I'm at an outreach event, I have to do a dance. What do you think? You want to try? I will warn you, this demo is great but unreliable because we never know how long to wait because the pumpkins are different sizes. So yeah, let's try it. Yeah, let's do it. Woo! Oh, that was great! Thank you so much. Happy Halloween, everybody.
All right. Well. Hey, thanks, guys. Hey, a round of applause for our demo. And again, get some cookies if you want some snacks before your next class. Happy Halloween, guys.
this one you drew this, but then you said it can't have two oxygen at once because the octane can't stretch. But how? But if they're 1, 2, 3, 4, 5, like 1, 2, 3, 4, 5. If they had another third double bond, how would the octet be stretching? Because they would still be less than 8.
Oh, so the octet usually have to take the entire, like all the electrons in the bonding pairs, and so not like cutting in half. So when you cut in half a formal charge, you got to then step back and count all the bonding pair electrons and lone pairs towards the octet. So if you make another double bond, you have 10
Oh, okay.
electrons.
Look at that.
Thank you.
Oh, you're welcome. Okay.
Just confused the structure of nitrate. So wouldn't it be better to do 2 double bonds? Because then that would make nitrogen have 5.
It would, other than it then would have 10 total electrons surrounding it.
Oh, that'd be bad.
And so nitrogen's small. So the reason why second row don't expand the octet is not that it's too small.
Okay.
Look at the extra electrons around it. As atoms grow bigger, we can expand octets.
Okay.
Well, in some Lewis structures we do. I still think maybe in some of them they're not as good. But even in the Lewis structures that are valid that have an expanded octet, it's because the atoms are bigger, allowing these electrons to like spread out.
Okay. Thank you.
You recognize the alphabets?
I don't know. I knew it was a costume that came up earlier, but I couldn't figure it out. Oh, okay. Gotcha. You know, I didn't watch that as much as I should have. That's funny. Yeah, great costume. That's cool. Yeah.
Thank you for the cookies.
Right, was there more?
What's your question about?
So Jim Tressel was a coach here. He got fired in 2009. The joke is he got fired because players are getting tattoos, and there's a big tattoo gate scandal, and so he ends up getting fired over it. So I have some tattoos if you guys like want a free tattoo. Like what's one is Woody Hayes, and like so like Woody Hayes got fired for punching a player. I don't know if you guys know this. You know that story? So like in a bowl game, Clemson intercepted a ball and goes out on the sideline, and the guy gets right up to Woody Hayes' face and kind of taunts him, and Woody Hayes decks the kid, and then he got fired the next day. But the thing to do would be dress up, not just dress up as Woody Hayes, but have that kid from Clemson show up and just get in my face and like pretend deck of the. I mean, nobody would understand it though. It's like you'd have to know the history really well.
Yeah.
Otherwise, you'd be like, "Look, I'm just He must really hate Clemson costumes." But anyways, I'd have to help me.
Any of these things back there?
Oh, I think I got it. Were you aware of Jim Tressel? Have you,
Pardon me?
were you in Ohio State, like, man, for a long time?
Not really. Like, got it, but you can say.
It's actually funny too, because like I got a sweater vest for Christmas the year he got fired. And so somebody got it for me, oh, you know, like a Jim Tressel sweater vest. And then he gets fired and, well, you know, not exactly wearing the sweater vest often. I'll take those. Oh, thank you. And then I had gotten like, actually the Terrell Pryor football jersey too. He was the player who got suspended, and then